Hello everyone and welcome to Machine Learning Tutorials. In this tutorial, we explain how to properly classify images using machine learning and TensorFlow Python library. That is, we will present a hello world example of machine learning. Let's immediately start with the problem formulation. We are given images of handwritten digits and corresponding labels. The labels are 0, 1, 2, 3, 4 until 9. Our goal is to develop and train a machine learning model to accurately predict a digit on the basis of a given image. Here's an illustration of the problem formulation. For example, let us assume that we collected images of handwritten digits. In practice, you can ask your friend or some other relative to write digits by hand. And then what you will do, you will take the images of these digits and you will simply scan them or you can simply take photos. Then you will segment these images such that you nicely crop them and such that every image represents a digit. Then you will label these images. For example, this image will be labeled as 5. This image, since it represents 0, will be labeled as 0. And then this image will be labeled as 4. Then, these images and these labels create, or better to say, represent a trained data set. This trained data set is used to train a machine learning model. That is, a machine learning model and the machine learning algorithm will learn how to properly classify these images on the basis of the images and labels. Classification means that for a given image, you can properly determine the label. Okay. So once we train our machine learning model on the basis of the trained data set, we are given the following problem. We are given an image of a digit that's not used in the trained data set. That is, that's not being used to train the machine learning model. And then our machine learning model should be able to accurately predict the label of this image. That is, if I'm given, or better to say, if I give to my machine learning model this image that obviously represents the digit 1, the machine learning model should be smart enough to determine the label and to say that the label is 1. And this is what we want to achieve in this tutorial. Okay, here's the standard procedure that we will follow to develop, train, and test our machine learning model. First of all, we will load the necessary libraries and packages in Python. Then we will load, inspect, and prepare the data sets. Then we will split the data set into train and test data subsets. Sometimes we will have 3 data sets, train, validation, and test. However, in this tutorial, we will just use train and test data sets. Then we will create our neural network model. Then we will train the model. And finally, we will test the prediction performance of the trained model by using the test data set. Okay, so let's start. Before we start with explanations, we need to mention that a link to all the codes developed and presented in this video tutorial is given in the description below this video. In this tutorial, I will use Anaconda and a very useful Spyder Python editor to develop and train my machine learning model. Consequently, I need to start Anaconda. To start Anaconda, click on Start and search for Anaconda. And you will see Anaconda Navigator. Okay, if you don't have Anaconda installed on your computer, then I created a separate video tutorial explaining how to install Anaconda and Anaconda Navigator. You can find a link to that tutorial in the description below this video. Okay, so click on Anaconda Navigator, and here you should be patient. It takes some time. Okay, our first step is to actually install TensorFlow. To install TensorFlow, you need to click over here on the environments. Then you need to click here on base or root environment. And here you should be patient. And then click on this green play button and click on Open Terminal. What you can see over here is a command prompt, and this base means that you're in the base virtual environment that's actually being created in Anaconda. So what will happen over here is that I will install TensorFlow. To install TensorFlow, I need to write pip install upgrade TensorFlow. And here I'm installing a CPU version of TensorFlow. However, you might also consider to install a GPU version if you have a powerful graphics processing unit. Okay, so let's run this command. And over here you can see that all the requirements are already satisfied. In my case, this is because I already installed TensorFlow before creating this video tutorial. However, most likely in your case, you will see the installation progress. So wait until the installation is completed and then continue watching the video tutorial. Besides installing the TensorFlow, we also need a few standard Python libraries. First of all, we need to install NumPy. Let's do that. Pip install NumPy. And as you can see over here, the requirement is already satisfied. However, in your case, you might see the installation progress. And we also need matplotlib. So let's type pip install matplotlib. Okay, and you can see that this requirement is also satisfied. However, in your case, wait until the installation is completed. Okay, now we are good to go. Next, go back to the Anaconda, click on Home, and let's start Spyder. You need to click on this icon over here. Spyder is a very powerful Python development environment and editor. I like it a lot since it reminds me of MATLAB and it's very easy to debug Python code in Spyder. So click on Launch to start Spyder. I like to start Spyder from Anaconda since in that way Spyder will be able to see all the libraries installed from Anaconda basically. Okay, so I will erase this comment section and let's start with coding. The first step is to import the necessary libraries. First, let's import TensorFlow. This is how we usually import TensorFlow as TF. Then the next step is to import Keras. From TensorFlow, we will import Keras. The next step is to import layers. So we will type from TensorFlow.keras import layers. Okay, finally, let's import NumPy as NP, and let's import the plotting tools. Import matplotlib.pyplot as PLT. Okay, let's now evaluate this piece of code. I will simply select it, then do the right click and click over here, run selection or current line. And you can see over here that we are able to import everything. Here, just be patient. Okay, good. However, before we continue, let's double check once more that we were able to properly install and import TensorFlow. To do that, we simply need to run this command. Over here, I will print the current TensorFlow version. And you can see how I do it over here. So let's evaluate everything and let's see the output. Here it is. We can see that the current TensorFlow version is 2.17.0. This means that we have properly installed and imported TensorFlow. Let's continue. The next step is to load the dataset. In this video tutorial, we are using the MNIST dataset consisting of images of handwritten digits and the corresponding labels. to load this data set, we will type this, keras.datasets.MNIST, and the output will be the MNIST dataset. Namely, Keras and TensorFlow come with several datasets that are used to compare the performance of different machine learning algorithms. And one of these datasets is the MNIST dataset. Okay, once we load the MNIST dataset, we need to extract the train and test data subsets. To do that, we need to call the function loadData, and this function will return two tuples. The first tuple will consist of train images and train labels, and the second tuple will consist of test images and test labels. Okay, so let's evaluate this and let's investigate these data sets. First of all, let's see the shapes. This is very important. Train images.shape. Okay, so the train images dataset consists of 60,000 images where the dimension of every image is 28 by 28. Okay, good. Let's see the train labels dot shape, and we can see that the shape of train labels is 60,000. That is, for every image in the train images we will have a label. Okay, this is very important. So let's see the test images. The test image is actually an array that has 10,000 images, where every image again is 28 by 28, and let's make sure that the label in the test data set has appropriate dimensions, and that these dimensions are actually consistent with test images. Yes, we can see that we have 10,000 labels. Okay, so let's pick a single image and let's investigate a single image. Let's call our image example. And to pick this image, we need to write train images. And over here, I will select the first image. Okay. Then I will also select label example for the corresponding image. So I will use trained labels and I will select the first label. Okay, so let's see our image. If I now simply type here image example, I should see my image. So here it is. Interesting. It's actually a matrix or a two-dimensional array. I can also explore the shapes of this image by typing this. And here it is. It's actually a matrix with 28 rows and 28 columns. The next step is actually to visualize this image. To do that, I will use plotting tools. So what I will do first, I will define a figure, and the figure size will be 6 by 6 inches. Then after that, I will show the image by calling the function image_show, and I will specify the image, and I will simply call plot.show. Okay, so let's see our image. And here it is. Wow, it looks like number 5. And let's make sure that the corresponding label is actually number 5. So let's look into the label example, and we can see that the number is actually number 5. This is very interesting. So let's pick some other image from the trained image dataset. For example, image number 10, and let's see the label. Okay, let's plot this image. This looks like number 3, right? So let's see the label. And the label is actually number 3. So let's pick another image, for example, 100. Why not? And we can see, wow, this is difficult to actually distinguish. However, let's see the label. The label is 5. Yeah, it looks kind of like 5. Okay, let's continue. Let's further inspect our data set. Let's again see our image example. We can see that it's a matrix. And let's see the minimum and maximum values stored inside of this matrix. So I will simply type image example, and to see the max value, I will call the max function. And let's evaluate this. And we can see that the max value is 255. And let's see the minimum stored value. The minimum stored value is 0. That is, all the entries inside of my images or image matrices are from 0 to 255. However, in order to be able to properly train and test our model, it's very important to scale these entries. The entries should be between 0 and 1, and consequently, let's scale all the entries to be between 0 and 1. And let's do that for both the trained data set and the test data set. The process of scaling is actually called the process of normalization in the machine learning literature. So let's do that. Here's how I can do that. I will say that train images are actually train images divided by the maximum value stored in the train images, and similarly the test images will be test images divided by maximum value. So let's do that. And then let's finally pick one image from the transformed image data set, for example the first image, and let's look into the max value. And we can see that the max value is now 1, and let's see the min value. And the min value should stay the same. That is, it should be 0. Perfect. Let's continue. The next step is to create our machine learning model. Here's how we do that in TensorFlow and Keras. We use the function sequential from keras.models, and this function returns our model object. The sequential function is used to define sequential layers. And the layers over here are separated by commas. In our case, we actually have 4 layers. But wait a second. What is a sequential model? Over here, I will illustrate graphically the sequential model. In our case, we will have 4 layers. Here's the first layer. Let's call it 1. Here's the second one. I will call it 2. Third one. And the fourth one. A sequential model means that the output of one layer is the input of another one. So the output of the first one is the input of the second one, the output of the second one is the input of the third one, the output of the third one is the input of the fourth one, etc. Okay, in our case, the input is actually a matrix with a dimension of 28 and 28. Let me just change the color over here. Then, this is our input. Now, our first layer is actually a flattened layer. This layer will actually flatten this image such that the corresponding or the resulting vector that results from this flattening is compatible with other layers. And that's, you need to always to use flattened layer when you have two-dimensional images. Okay, then the second layer is actually a dense layer, nothing special, just a dense layer of neurons. Then the third layer is a dropout layer. This dropout layer will actually set to 0 some of its inputs. That is, the outputs of our second layer, that is the outputs of the dense layer, will be set to 0 by this third layer. And the probability is 0.3. That is around basically certain amount of neurons will be set to 0 with this frequency over here. In this way, we actually reduce the number of inputs and outputs. That is, we reduce the number of dimensions in our neural network. In that way, we can speed up the training process, and in some sense, we can also avoid overfitting. And finally, we have a final layer, that is the fourth layer, that consists of 10 neurons. So we have first one, second one, third one, fourth one, fifth one, sixth one, seventh one, eighth one, ninth one, and 10th one. Okay, so this is our output layer. For the sequel, it's very important to properly understand our last layer. Consequently, let's illustrate this last layer and let's explain it thoroughly. In the last layer, we have 10 neurons, or 10 points, or 10 nodes. First one, second one, third one, fourth one, fifth one, sixth, 7, 8, 9, and 10. Every neuron in this last layer corresponds to the label. That is, the first one corresponds to digit 0, then 1, 2, 3, 4, 5, 6, 7, 8, and 9. Notice over here that we specify the activation function to be softmax. The softmax will return 10 probability scores, quantifying the probability that a given image is predicted digit from 0 to 9. Okay, so what will happen over here if I give to my neural network an image representing, for example, number 9? If this neural network is properly trained, then this last layer and the corresponding neurons should return the probability that this image, that is the input image, is equal to 9. For example, it might happen that over here the probability will be 0.01. Then the probability that this image is actually 1 will be 0.05. Then the probability that this image is actually 2 will be, for example, 0.1. Then the probability that this image is equal to 3 might be, for example, larger, 0.15, since it looks like that 3 is similar to 9 if we kind of neglect this lower part, etc. Maybe you will have lower probabilities, and over here you might have the largest probability, for example, the probability of 0.6. And the softmax function achieves that. That is, it achieves that the outputs are probabilities, and if we sum all the outputs of the corresponding neurons, we should get 1. Since the probabilities, the sum of the probabilities for events should be equal to 1. And that's it. That's the main idea. To summarize, the outputs of our neural network are actually probabilities that the input image is the corresponding digit. Again, if you see as a third output 0.15, then there is a 15% of chance that this input image is actually 3, etc. Okay, this was very important to understand, and spend some time to properly understand this. Let's continue. The next step is to compile our model. First of all, we need to select the optimizer. In our case, we are selecting the RMS prop. This is a very standard optimizer often used in machine learning community. Then we need to define a loss function. A loss function in our case is sparse categorical cross entropy. And the loss function quantifies mathematically the difference between the prediction and ground truth. And as a matrix, we use accuracy. In our future tutorials, we will thoroughly explain the optimizer, the loss, and metrics. For the time being, let's just continue, since the purpose of this video tutorial is to quickly teach you how to perform machine learning training in Keras and TensorFlow. And finally, let's fit our model. To fit the model, we need to call this function model.fit. The first input is train images, the second input is the train labels, the number of epochs is equal to 50, and the batch size is 128. Over here, you can change the epoch number and you can change the batch size. By increasing the epoch number, you will actually increase the time it takes for the network to be properly optimized. That is, you will increase the optimization time. And over here, batch size is another parameter that you can play with. Okay, so let's run everything from the beginning until here. And let's see what will happen. Okay, and over here you can see the progress of optimizing the network. You can see the accuracy measure, and you can see the loss, and you can see the epoch number. And then I'm here using a CPU, I'm not using a graphics processing unit, so it will take some time to optimize our network. And that's it. It's not bad. Let's see the final value of accuracy. The final value of the accuracy on the trained data set is very good, 0.9906, and we can see that the loss, that is the value of our cost function, is 0.02. These are very good results. However, be careful over here. These results might be misleading, since I can always spend a large amount of time to optimize my network on the trained data set. The true measure of the prediction accuracy and the performance of the machine learning model is the test data set. That is, we have to use images that are not seen during the training process. Okay, so let's perform the final test. Here's the code that I will use. First of all, I will create a small subset of the larger test data set. I will pick 20 samples, and this is my ground truth. I will take from test images first 20 images, and I will take from test labels first 20 labels. And over here, I'm going to do prediction on the basis of this small data set. To do that, I will call my model, and I will call .predict, as the input will be test images subset. So what will happen behind the scene? I will present to my trained network images from the test data set. That is, the images that are not seen during the training process. That is, the images that are not used during the training process to optimize the network parameters. And now, this model.predict function will return the prediction labels. So let's run this and let's see the output. Okay, now let's see what are the actually prediction labels. So what I will do, I will simply do this, prediction labels over here, and I will take the first prediction. And let's see what do we see over here. I see a bunch of numbers over here. So what are these numbers? Well, these numbers are actually the probabilities that the corresponding image from the test data set is actually an image represented by a certain digit. So let's see, first of all, the image. Test image subset, and let's see the image. Okay, so here's the image. However, let's print out this image. To print out this image, we will simply define our figure. Let me just copy and paste the code that I used. Here it is. Then what I will do, I will test image subset. Let's just pick the first image and let's just plot it. Okay, so it looks like that this image is number 7. However, let's compare this with the prediction. So let's again prediction label 0, and let's see. Okay, so the probability that this image is 0 is very low. The probability that this image is 1 is very low. The probability that this image is 2 is very low, similarly 3, similarly 4, similarly 5, similarly 6, and we can see that the probability that this image is 7 is huge. That is, it's equal to 1. And consequently, the output is 1, or should be 1. So what we can do over here on the basis of the prediction label, we can simply do this, .argmax, and let's see what it is. And the output is 7. The argmax function returns the index of the entry that has the max value. And in this case, it's the 7th entry, and consequently, it's 7. So the prediction was good. However, maybe we were just lucky. Let's look into some other image. For example, let's look into the image number 6. Let's plot this image. Here it is. So this is 1. Okay, let's make sure that the prediction is correct. So let's do that. And over here, we should see 5. So let's see. The probability that this image is 0 is, let's see, is very low. It is almost 0. Then the probability that this image is actually 1 is almost 1. Don't be confused by 9.99. Look here that this is 10 to the minus 1. So the probability is 1. So let's again run this. And we should see 1. That's correct. Good. Now let us do this procedure systematically for all the images in this small data set. So what I'm doing over here, I'm defining this vector prediction final labels. And inside of this for loop, I'm simply computing the argmax and I'm returning the maximum value of the probability. So let's run this. And let's see what do I have as the output. The outputs are actually the digits that have the highest probability. Now, you can see the test label subset is actually the test label subset extracted from the test data set. So let's compare these two data sets. That is, let's compare our prediction with the grand truth. I can do it like this. And I'm defining a new Boolean array that will tell me if the predictions are correct. So I have true, 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 so everything is true. Now, let us use the original test data set to evaluate our model. To evaluate our model, we use the function model.evaluate. As the first input, we provide test images, and as the output, we provide test labels. And the output of this model.evaluate is the test loss and test accuracy. So let's see this. Okay, so let's see the test loss is not bad. And let's see the test accuracy. The test accuracy is 0.98. So we are able to accurately predict 98% of the images. And that's relatively good result. Okay, that's all for today.